this. Okay. So this can represent pressure loading. So wind pressure, for example, wind pressure when wind blows and then strike this building, so it will create this kind of loading. This is a pressure, wind pressure pushing against the frame. This is pushing, and then wind can cause suctions. Wind can cause suction against some members. That is why sometimes when during strong wind we see the roof, zinc roof being blown away. Zinc is being detached from the roof structures because the wind is causing suction pressure, and if the zinc is not held down properly, then the zinc will fly away, which is caused by suction. This again suction here. Suction. There is a kind of pressure, but suction. It can cause whatever detached here to be detached from that particular part of the building. So this is one example that we want to look at, and then the dimension 2.4 meter, 2.4 meter, 3.6 meter, and then the height of this inclined part, the pitch part, the roof here is 1.8 meter. So first, let's check the statical determinacy. This is to refresh yourself again. So there is a hinge. So don't forget, you separate it at a hinge here. So you separate the hinge, then this blue color, these internal forces appear. There are two here. Magnitude the same, direction different. So all together, the red one, there are 4. The green one, there are 2. So unknown forces, there are 6. Equilibrium equations. So you separate at the hinge, so you have 2 parts here, the blue parts here, so there are 2. So you get each of that blue part, you have 3 equilibrium equations, so equilibrium equation, there are 6. So because this number of unknown forces is equal to number of equilibrium equations, so statically determinate frame. So this is a process of checking for statical determinacy, which you should be familiar with by now, and for problem with hinge. Separate them at the hinge then. So now let's go to a bit of explanation about the characteristic of the loading in this particular example. So this is load on inclined members. We have seen this just now in the second example. In the first session that I have, the last example, you have an inclined members, and the loading acting is 90 degrees to that inclined members. And the intensity here is 0.7 and the other side is 3.3. Direction of load is inclined to member axis directions. So this is a free body diagram. Now this is the first solution process. So we need to find, what we want to find is AY, AX, CY, and CX. The reaction forces at the support, the pin support, 2 pin supports here. We do not need the internal forces at the hinge. Okay. So the things that we need to calculate is AY, AX, and CY, CX. That is the thing that we need to calculate. So next, we will then look at first equilibrium equations. We take moment at C, considering the free body diagram of this whole frame, of the whole frame here, and take moment at C. If you take moment at C, because this and this, they are at the same height level, if you take moment at C, so you do not need to consider CX and CY, of course, and you do not need to consider moment caused by AX for this particular case, because A and C, they are located at the same height level. So AX is passing through point C. The line of action of AX is passing through point C, and you do not, it does not cause any moment at C. So if you do this, then eventually we get AY directly. So it is good to find one equilibrium equation that we can start with in the process of solving for AY, AX, CY, CX, and you find one which you can get any one of that directly. So in this case, if you take moment at C, you will find AY. Similarly, if you take moment at A, you can find CY directly. So let's look at the detailed one here now. So the detailed moment caused by each of the forces which appear on this free body diagram, and we will pay attention, specific attention to how to consider this loading acting on these inclined members. Now, this 4-3, this is 4-3 comes from where? 4-3 here comes from this triangle here that we are deriving. We get it from the dimensions given to us for the hinge. You look at this diagram here, this is a bit small diagram here. This is given as 2.4 meter, and this is given as 1.8 meter. So if you use Pythagoras theorem, then you can get this is 3 meter. The inclined length of this member is 3 meter. 2.4, 1.8, you can also write in terms of the ratio of this triangle to be 4, 3, and 5. 4, 3, and 5. If you divide this with 0.6, then you get 4. If you divide this with 0.6, 3. If you divide this with 0.6, you get 5. So the ratio becomes 4, 3, 5. So this is where the 4, 3, 5 has come from. It is not all the time 4, 3, 5. You have to get this information from the dimensions of this frame given to us, or you can find this angle here. Find this angle. For example, tangent of this angle is equal to 1.8 divided by 2.4, then you can find that angle. And that angle is needed when you want to find the component of this UDL in X and in Y directions. Now here, we put this as 4, 3. This is for the inclination of the member. But when we want to find the component of the force, then we need to rotate this. Remember what we discussed, I think, last week, when I discussed with you yesterday in one of the lectures, how to consider this inclination given like this when you want to find the component of the forces in X and Y directions. So when you want to find component for this distributed load, the equivalent load of this distributed load here, then we need to make use of this triangle where the horizontal distance now become 3, vertical become 4, instead of horizontal 4, vertical 3. Because this is for inclination of this member. What we need is inclination of the force. So that is a bit about the other things that we need to know in order to write down this equilibrium equation for moment. Now let's go into one by one. So the first one is AY. This is moment due to AY. The second one, this is moment due to this. Moment due to this UDL, which is acting in horizontal directions. Class, if you have any questions, if you can't see the screen, please notify me. Okay, I'm showing you now the example on this gable frame. So you have this is due to these parts, which you should know by now how to handle this. And then next one, this part. This one is come from here. This one is due to this. Now we pay attention to this second line here, So this one is due to the moment, this is considering the moment caused by this one. Moment caused by the loading acting on these inclined members. So first we get the horizontal component, which is the total load. 0.7 multiplied with 3 is the total load. 0.7 multiplied with the length of this is 3. The length of this is 3, not 5, yeah? The length of this is 3 meter. So 0.7 multiplied with 3, and to get horizontal component is 3 over 5. So you get the horizontal component, and the perpendicular distance will be this distance. The blue color here, this distance. So half of this height, which is 1.8 divided by 2, and the height of this vertical member is 3.6. And it is causing, we take moment at A, so it's causing clockwise moment. That's why it becomes negative. It's causing clockwise moment at A, so it becomes negative. Okay. So next is this one. This is causing a moment clockwise, yeah, clockwise moment, correct. This is, we take moment at C, sorry, we are taking moment at C, sorry, we are taking moment at C, so it's causing clockwise moment at C, that's why it becomes negative. So the second term here on this second line, indicate here, this is moment caused by the vertical component. So find the vertical component of the force first, 0.7 multiplied with 3, this is the total force. Get the vertical component, so it becomes multiplied with 4/5. Then the perpendicular distance will be this distance. So you draw a line parallel, draw a line passing through this vertical component and another line which is parallel to this passing through point C, and this will be so the blue line here is the perpendicular distance. So this perpendicular distance will be half of this distance, which is 2.4/2, plus this horizontal distance here, which is 2.4. So this is a perpendicular distance multiplied with the vertical component of the force. You get the moment caused by vertical component of this inclined force. And it is causing counterclockwise moment. It is causing counterclockwise moment at C. That's why it becomes positive here. So the same thing if you go to the next line, that gives you this force. Now this force, the direction is acting away from the member. So the horizontal component, the vertical component is in these directions. So we look at it one by one in the same way. The horizontal component, the total one is 3.3 multiplied with 3, then multiplied with 3/5. This inclination is the same. So multiply with 3/5, then we get the horizontal component, and don't stop here, multiply with perpendicular distance. This blue color here again, this is the perpendicular distance. And it is causing clockwise moment at C, so negative. So the next one is this, the vertical component, total force, multiplied with 4/5, get the vertical component. Then the perpendicular distance will be, you draw a line, if I draw a line passing through this, and another line parallel passing through C, parallel to this line. So this is the perpendicular distance, and that perpendicular distance is half of this horizontal distance, which is 2.4/2. And now this is causing clockwise moment also at C, around C, so negative. So the second line and the third line here is to consider the moment caused by this distributed load and the moment caused by this distributed load at point C. And here we get the component, the moment caused by each of the component X and component Y, and we sum them together to give the component caused by this distributed load. So we get answer AY negative 15.705, or the correct direction is acting downwards, and AY with the magnitude 15.705. So now we have already solved for AY, and the correct direction indicated here is 15.705. So next, remember our aim is to find AX, CY, and CX. So the next one is we try to find and use a free body diagram and then find the equilibrium equation where you can solve AX, CY, or CX directly. So the next one that we can use to do that, if we make use of this, we break this, we separate this, we cut this at the hinge here, so we draw this free body diagram. So AX, AY, AX is unknown, AY already determined, and there is an internal force BX and BY. Now remember, we want to find AX, AY, CY, CX. We are not interested in BY, BX in this question. So remember that we want to find AX now in this free body diagram. So the loading acting here, and dimension. Here I show to you this diagram. For this particular free body diagram, in this case, if you want to take moment at B here, then here we can consider moment caused by this directly in terms of this, and no need to use the component. You can also use the component X, component Y, moment caused by component X, moment caused by component Y at point B. It will be the same as if I consider directly this force and the perpendicular distance directly in this way. Here I can use perpendicular distance directly to be half of this length, because this is acting 90 degrees to this member. So this half of this length becomes the perpendicular distance for this force to point B. So this is what we have used in this example to get the moment. We do not use change it to horizontal, change it to vertical, because that will take more time. This is more direct. And this is the importance of getting back to the basics of moment. Force multiplied with perpendicular distance. So now let's look at how to get AX. This is just take moment at B. Okay. Take moment at B. Take moment at B. Then consider all the moment caused by AX, caused by AY, caused by this distributed load 3.7 kN per meter, and caused by this load acting on this inclined member. So this is how. So this AX 3.6 plus 1.8, this is a moment caused by this AX. The perpendicular distance to B will be 3.6 plus 1.8. And the second one, 15.705. So the perpendicular distance will be 2.4. And we take counterclockwise as positive, so this is causing counterclockwise, this is also causing counterclockwise moment at B. So this one, 3.7, 3.6, this is coming, this is the moment caused by this total load and the perpendicular distance. So half of this height, this is 3.6 over 2, plus this height, 1.8. So we get this. And this one here, these terms here come from this, where directly we, based on the definition of moment, force multiplied with perpendicular distance. So it is easier to consider in this way for this case now. So 0.7 multiplied with 3 multiplied with perpendicular distance will be half of this length of this member. This inclined member, the length of this inclined member is 3, so half divided by 2. So multiplied with the force, you get finally AX negative 16, and the correct direction is not to the right but to the left with the magnitude 16.443. 16.443. So that is how we get AY and how we get AX. Okay. So let me pause for a while, and then if you have any questions before I proceed again to the rest of the solution process. Any question on this so far, class? So this is how we consider the vertical example with inclined members and together with a hinge. Together with a hinge. Okay. If any question, please, as usual, you can always put a message on the chat and try to get back to you. Or you can switch on the mic and then say, Moshi Moshi, can I ask a question? Then you proceed to the questions. Okay. Once in a while, it's good for me to listen to your voice. Okay. So, any question, class? So let's proceed. If you have any questions, then you can ask me later when we pause again. And now I'm sharing you back the screen. I hope you can see the screen. Now, we have solved for AY, we have solved for AX with the directions. So AY is acting down, AX is acting to the left. So we are left with CY and CX. So here, take note again, class, when we are using free body diagram where we separate at the hinge and we make use of this part only. So we put a symbol here to represent we are using actually this part after we cut left-hand side of the structures after we cut at the hinge. So we put AB here. So we make use of this part only. The next step is to get CY and CX. So to get CY and CX, we can get force equilibrium equation in X direction, we get CX. Force equilibrium equation in Y direction, we get CY. So that in that sequence. So let's look at this. So to get CX, we take force equilibrium equation in X directions. So now I show you here how the calculation. So this one comes from where? This one comes from this reaction force. We take to the right as positive, so this becomes negative. Next one, this one comes from this. And then this one, let's come back to this later. This one comes from here. And plus CX, of course. And this second line here, this one, I show you the arrow here. This one comes from here. And this one, the brown color, and come from this part. So this one, take the component of this force equivalent to this UDL acting on this inclined member in X directions. So the total 0.7 multiplied with 3, multiplied 3 over 5, get the horizontal component. And it is pointing to the right, so positive. The same thing here. For this one, 3.3 multiplied with 3, which is acting 90 degrees, and get the horizontal component multiplied with 3 over 5. And it is acting against to the right, so become positive. So we solve this, you get CX negative, then the direction assumed, which is not supposed to be the correct one, is to the left. So this is how we consider this UDL acting on inclined member perpendicular for this and for this in force equilibrium equations. So finally, only CY left. So CY left, so as I mentioned, we take summation of forces in Y directions. Consider going up as positive, so negative 15.705 comes from here. This one negative comes from this, the Y component of this inclined UDL. And this one is the Y component of this 3.3 kilonewton per meter. And the direction of this is going down. The direction of this Y component is going up. So that's why we become positive. Plus CY we assume as going up. Now this time we are correct. The CY is positive 9.465. So the direction is going up. So with that you complete all the AX, AY, CX and CY. Then we put them together here. This is an answer that we have already obtained so that it is clear. The reaction forces here. Then if we want to do checking, then we take moment at B, at this hinge here, considering the whole frame. So we take all the moment caused by, you evaluate all the moment caused by this load, this load, this load, including the reaction forces, then we can then get the, we can then get the summation of moment at B, then it should be equal to 0, approximately equal to 0. So that is checking. That is checking. So this is how we solve these problems. And here this problem characteristics is inclined members and also with hinge. So when you have hinge, then we will need to make use of the condition of the hinge to help us. So this is where we make use of it. These steps here, when we want to find AX, and we find AX. Okay, so there's one question here. Okay, let me pause for a while and then answer the question.